Hi, boys. Hope you're doing well. In this video, I want to introduce to you a little different perspective on something we've done before. And recall before we've done the instantaneous rate of change of a function or the slope of a tangent line at a point. And now we're just going to generalize that. So let's suppose that I'm trying to find for a function, and that function has to be pretty well behaved, and we'll talk about what that means later. And let's say we want to find the slope of that tangent line at a point, right? And so we called that point A, and I found that point on the curve. So this is what I'm looking for, right? Slope of that tangent line. And we've called that M for slope sub t in the past. And what we've done is we say, okay, let's pick another point beyond A. And the x value for that point is A plus h, right? We're going to find that point on the curve where the x value is A plus h. And then we find the slope between those 2 points. We call that the slope of the secant line. Right? In order to find the slope of that secant line, you got to know that essentially the 2 points between which we're evaluating that slope. And so for this point here, if the x value is A plus h, then the y value is f of A plus h. And for this other point of tangency here, if x is a, then the y value is f of a, right? And so what we did is we said, okay, let's first find the slope of this secant line here, right, between those 2 points. And we said, all right, well, that's going to be just the change in y, which is that y value here, f of a plus h, minus the other y value, right? That's a change in y over now the change of x. Now the change of x is pretty easy because of the way in which we set it up. So the change of x is just going to be, well, a plus h minus a plus h minus a, and of course that just leaves us with an h. That's the difference in the two x values. Okay? So as that sits and looks now, we call that the difference quotient, blah, blah, blah. But really what that means is that expression is the generalized slope of the tangent line at x of a. But yet, it's not yet the slope of the tangent line. We have to bring those 2 points together. And right now, it's a slope of the secant line. And so I don't want the slope between these 2 points. I want them close together. And now I want the slope between the 2 points that are virtually on top of one another. All right? Not quite, but virtually, arbitrarily close. And so the way we drag those 2 points onto one another is we take the limit as h goes to 0 of still the slope. Okay? And so this in the past we've called the slope of the tangent line at a point. Okay? Now, if we go through that same process and generalize, now we can say, all right, what if we want the slope of the tangent line at any point to a curve? Right? So now it's not at x equals 2 or x equals 3 or x equals a. Now it's at any point. So let's generalize a little bit. And so let's just say at x. We want the slope of that tangent line at x. And so m, slope of the tangent line, or we could call it instantaneous rate of change, at any point, at x. And we can go through the same process. And we can say, all right, well, that would be the point of tangency, x, f of x. We're going to pick a point somewhere beyond that, and we call that x value x plus h. All right, so this other point here has x plus h as the x value, and f of x plus h as the y value. And we're going to find the slope between these 2 points. That's the average rate of change, or slope of the tangent line. And that slope is going to be f of x plus h minus f of x, that's change in y, over the change of x plus h minus x, that's just h. But right now, that's just a plain old boring slope of that dotted secant line, average rate of change on that function between these 2 points. So to make it the instantaneous rate of change at x equals x, we just drag these 2 points arbitrarily close together by letting h go to 0. And so what we have here is we have an x-containing expression rather than finding the numerical slope of the tangent line at a specific point. And what this is called is the derivative, which we note as such. And so this is what's referred to widely as the limit definition of the derivative. Okay? And so we say the derivative, that's called f prime. That's the derivative of f. And we note it as f prime. That's one way to write the derivative. And what the derivative is it essentially tells you the slope of the tangent line, or the instantaneous rate of change of the function, not at 2, not at 4, not at a, but at any point. So it's a formula, it's an equation, it's an x-containing, usually, expression that defines the slope of the tangent line at any point of the original function f. So let's do an example, shall we? I'm going to leave that up here. So if I said, what's the derivative? And that's another way of expressing the derivative. It looks a little bit like slope, right? Well, it should. So this means, what is the derivative of 1 over x? So really it says, what is the derivative of 1 over x? And this means with respect to x dx. I'm differentiating this function, 1 over x, with respect to x. And that will become more meaningful later as we uncover more of the calculus. Okay, so I'm finding the derivative of 1 over x. Okay, and so what I'm going to do is I'm going to use the limit definition for now. Very easy ways to do it. And I'm going to say, okay, that's going to be equal to the limit as h is approaching 0 of the function at x plus h. Well, the function at x plus h is just 1 over x plus h. Minus whatever the function is. Well, the function is just 1 over x. And then all over h. So that is the limit definition of the derivative of that function 1 over x. Okay, now you have to figure out what the heck that is. So we've been working through problems like this recently. And so I think the easiest way is to kind of pull that 1 over h out just so I can see what is really happening. So my first move here is just to write it a little differently. It's the same thing. And now my next move is to use a common denominator for what's within the parentheses. All right, the common denominator is going to be basically the product of those two denoms. And I have to multiply the first nugget by x over x. Minus, I have to multiply the second nugget by what's missing in the denominator. That's an x plus h, the quantity x plus h, don't forget that. And now I'm going to clean that up. And I get limit as h is going to 0. That 1 over h, which came from this original h in the denominator. Just pull it out. Wrote it a little differently. But in the numerator here, what's left is x minus x. Ooh, no more x's. Minus h. So there's only a negative h or minus h in that numerator. And ooh, wouldn't you know it? That's going to cancel here. Yes, sirree. And now I can substitute that 0 in for h because I have removed what was preventing me from substituting in the first place, the 0. That's that h here. That's gone. All right, so remember I'm plugging in a 0 in here. So I get a negative 1 on top. There's nothing left on top. Well, there's a 1 on top, not a 0. And then at the bottom I have x times x plus 0. So that's x times another x. That's x squared. So what I just showed is that the derivative of 1 over x is negative 1 over x squared. Okay? What that means is that it is this function, negative 1 over x squared, that will tell me the slope at any point, the instantaneous rate of change at any point of the function 1 over x. So if I said, what's the slope of 1 over x? When x is 3, just plug in a 3 to the derivative. So it's negative 1/9. If I said, what's the instantaneous rate of change of the function 1 over x? When x is 4, I'm going to plug a 4 into the derivative. Negative 1/16. So it's pretty helpful in many ways. And those ways we'll start to uncover more as time goes by. But anyway, that's how you find the derivative. Some of us like to be visual too. And we can certainly set up a drawing and go through the same process. Here's 1 over x. Right, so pick your point if you want, not 2 or 0 or 3, but I want to find the slope at any point x, right? So find that point x here, find a point beyond it. This was the point x, 1 over x, right? Because I'm on this function 1 over x. This here is a point 1 over x plus h. No, it's not that point. That's the point, sorry. X plus h, 1 over x plus h. Right, and we can proceed in the same way we did before. So for those of you who are more visual, here's the derivative. I would say, okay, the derivative of 1 over x, using the limit definition and using this visual aid, is going to be the limit as h is going to 0 of the change of y, 1 over x plus h minus 1 over x, change of y, over change of x, which is just h, and then we take the limit of all that as h is going to 0, right? Which we just did. So there's a visual interpretation as well. So if you need to draw the function and draw those 2 points, just be careful if we're finding the derivative, those 2 points are going to be an x and an x plus h for the x values, right? Not a 2 and a 2 plus h, or a 4 and a 4 plus h, okay? Either way, slice it. Here is a limit definition of the derivative. Here's how we can use it algebraically. There are much easier ways to do it, which we'll get into. So have a great day. Enjoy this. I'll see you in class soon. Bye-bye. Let's go.